What a drizzly, horrible, miserable day. Probably a good day to be doing electronics, actually. Except I've got to go to work in about half an hour. But anyway, I really, seriously need to weed this garden. Ugh. I'll get there. Well, I'm looking back at this 555 timer indicator relay circuit that I did in a previous video, which I'll link in the description. But I've actually made some progress. I have actually fixed the issue with the two panel indicator bulbs coming on at the same time when it's initially clicked on, and sometimes both coming on when it clicks off. So I'll just connect. So that one's flashing away. I'll do the other side. And as we can see, I don't know if you can see the bulb because my hand's in the way. You might be able to see it. Might move that bulb over here somewhere. It's not flicking on when you either connect or disconnect, and yeah, that fixed that problem. It still does with LEDs because the current draw is too low. All I've gone and done is I've added a PNP BJT transistor here, a TIP42C, and the base is driven off of the NPN transistor down here, the BC547, which drives the relay. And I guess because of how much current the relay requires to actually pull in is preventing the base of this transistor being turned on as quick, for want of a better term. So it's like probably adding a couple of milliseconds delay there before current can flow between the collector and emitter, or emitter and collector, whichever way you want to look at it. So it prevents the bulbs turning on at the same time as the main flashing bulb is turning on, so as if you were using a mechanical switch like a relay. So that's fixed that problem. And I have no idea what the hell that was. Anyway, I'm going to move on to something else that I want to try out in this experiment here. I want to try adding in a current sense circuit that will flash the bulbs quicker if one of these 21 watt globes was blown, assuming that you've got two of them on one side, which most cars do. So as soon as one bulb goes away, well, it will flash the thing faster to let you know that you've got a blown globe. So let's get going on that. Pizza. Oh yeah. Greetings, the Astro 30 here yet again, and welcome back to AEL. Now, if you're new to this channel, please consider subscribing below if you haven't done so already. As I said in the intro there, today we're going to be looking at revisiting this car flasher relay solid state implementation. Now, I already said that I've got the panel lights to work correctly using this transistor. That's now not connected to any lights at the moment. I can connect it back up in a minute. But what I wanted to implement was for the relay to flash faster when one globe is blown. So if you've got two globes in parallel, if you've got two globes in parallel on one side of the car, as normally it would be wide, there's usually three, but two of them are like 21 watt globes. If one of them blew, then you want this to flash at double the rate to indicate to you as the driver, oh, I've got a blown globe on this side somewhere. Which means you should get out and check your lights, which a lot of us are really lazy about doing. I rarely ever check my lights. Anyhow, So I've gone ahead and I've come up with a comparator circuit which I actually found online, and I'll link that in the description as well. And I made a few modifications to it. Now, I've got a shunt resistor here which is a 0.22 ohm 2 watt, which is way underrated. It does get quite hot if the circuit's running for more than a couple of minutes, so that may have to change. And that's being fed into one side of a comparator, which lives up here, as messy as that is. That's an LM393 dual comparator. And I will go through the schematic after I've drawn it up in KiCad correctly, and you'll see the changes at the end. So this is only going to be a short video. So I had to mess around with some of the values, well actually only one of the values. It was the pull-up resistor on the output pin 7 of the second comparator, which is connected to a NPN transistor down here, which is actually effectively bringing a 4.7 microfarad capacitor to ground, which goes back to the oscillator. There's another 4.7 microfarad capacitor in place of where the 10 microfarad used to live. So when this transistor is turned on and brings this capacitor to ground, well, we've now effectively put two of these 4.7 microfarads in parallel, and that gives us around about 9.35 microfarad, pretty close to 10. So it's not quite 10, but it doesn't seem to really visually affect the flash rate any different than the 10 microfarad versus 4.7 microfarads, if you get what I mean. So I'll demonstrate the operation of the circuit. In fact, I'll do it backwards. Say we've already got a blown globe. Okay, so I'll connect that to the circuit. See how it's now flashing quite fast. If I now connect my other globe, flashes normally. Disconnect it. Right, there's a bit of a delay there because there's a 100 microfarad capacitor here which is going to be holding a charge. So the comparator won't react fast enough for it to instantly tell you that the globe is blown. But the idea is when you actually flick the indicator on, that it goes tick 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 to let you know, yeah, I've got a blown globe. Or tick tock tick tock tick tock. That's my best imitation of a car relay turn signal flasher. That's all it's designed really to do. It's not designed to be perfect. So what I might do is I'll just connect the panel lights back up. Now that is my center point that goes over to here, because I want to make sure that all this circuitry works okay with each other, because obviously the panel lights being in parallel with the globes here is not going to work when both are joined to the output point, because, well, the two globes here are basically shorted out now. So this wire would go to this globe. Okay, so this one over here is the left-hand indicator, that one's the right-hand one. So I'll just turn the supply back on. So we should see this globe flash and that one flash, which we do. Now we should see the opposite. We should see this one flash and that one down there flash, which we do. So if we connect both of them up, well, those two globes go out now, obviously. Neat. So I'm not going to do that too long because of that shunt resistor. So really that shunt resistor needs to be changed, and the original circuit that I found said just using basically a piece of wire as the shunt. That has a minor resistance of about 30 milliohms or so. So a wire would be much more substantial, but I don't know how I'm going to get a shunt wire in there, because it'll have to be a fairly thick gauge wire, like at least capable of 7 amps flowing through it. I might be able to solder 2 leads onto a piece of wire and see if that works as a shunt. So that's going to be my next experiment, is experimenting with the shunt. Well, I've got a clip lead in there as the shunt, And well, yeah, it does work, but it's fairly long. I tried a short bit of tinned wire that didn't seem to work too effectively. The resistance is just way too low. So I'd have to come up with a better idea, but however, I'll just demonstrate that this is indeed functioning with that clip lead as the shunt. So if I disconnect the shunt, well, yeah, the circuit now fails to give power. But at least it's not interfering with the cancel circuit. Although that was flashing slowly. There it goes. I guess it's waiting for this capacitor to discharge plus these two. Okay, so yeah, it works with a piece of wire, but as I said, the piece of wire is way too long. Yeah, okay, copper wire is not going to work. It needs to be an alloy, nickel and copper composite, or constant wire, I think they call it. Constantan, whatever. Yeah, we need something like this, a proper shunt. It's made of copper nickel alloy composite, and these are 15 milliohm. So I might order some of them and try the experiment again. Okay, so I might as well explain what I've got so far. Here's the complete schematic. The oscillator is the same as it was in the last video. Nothing's changed there. Still got our ground reference detect transistor here, driving pin 4 of the 555. And we've got two capacitors now connected to pins 2 and 6. Both of them are tantalum, and the one on the reset pin is a 10 microfarad tantalum. Now the reason why they're tantalum is because they have a higher temperature coefficient, so they work better in extreme cold and better in extreme heat conditions compared to normal electrolytics. So that will keep the oscillation speed stable under those different conditions, because it is pretty hot underneath the dashboard sometimes. Forgetting about this transistor over here for a second, we've got a shunt resistor which I've shown as a 0.33 ohm 100 watt. That'll probably change. I've got some parts on order. I've got some 0.015 shunt wires coming and a 0.33 100 watt resistor. Now that might seem a bit large compared to using just a shunt wire. However, I found that using 0.22 ohm over here, well, the circuit doesn't operate, it just continues to flash at the fast rate. So that means that this circuitry over here would have to modify. Probably this resistor value here. Anyway, these are two comparators, LM393s, each half of the IC. This comparator is operating close to the supply voltage, which comes here on the X connection here and smoothed by this capacitor. So this is sitting close to 12 volt. The voltage flowing through this shunt resistor only has to change by a few millivolt before this comparator will go low. And if both of these input pins here are sitting at roughly the same voltage potential, then the comparator's output will remain high. That either high or low pulse is rectified by this signal diode on 1N4148, because we're only really interested in the positive going cycle. That will then charge this capacitor via this resistor to give it a more stable DC, which is compared on pin 5 here. If the compared pin, which is pin 6 here, which is tied high, and is set to roughly about 1 volt, and if the input pin here is higher than a volt, then the output will be high here. If, however, this falls to nearly 0 or below 1 volt, the comparator's output will be low. And the reason we use a second comparator here and this really weird looking circuitry here is this is basically going to be a buffer. So it either sees a on pulse or an off pulse. And that's all it produces, either on or off. Both outputs are tied high by these pull-up resistors, and The reason why this one is so high is because this base biasing resistor on this transistor here, which is supposed to be 10K, not 1K. I'll fix that later. I don't know why. I've just copied another resistor, probably this one over here, and I forgot to change the value, but it should be 10K. If this was lower, because it was originally 1K, well, this transistor is going to be turned on all the time, and the comparator is not going to do anything to that voltage. I don't know why. It's probably the way the comparator's output works, but it was always sitting around about 0.5 to 0.6 of a volt here at the base of this transistor, regardless of whether the load changed, whether we had 21 watt or 42. So I changed it to a 47 for the pull-up, and it works quite nicely. And all this transistor does is when this comparator's output is high, this transistor is turned on. Therefore, this 4.7 microfarad tantalum capacitor is pulled to ground, which is then paralleling it with this second 4.7 microfarad tantalum capacitor. And we get an effective capacitance now of roughly 9.35 microfarad, close to 10, what it was before. So we get the normal flash rate. As soon as the comparator sees a few millivolts difference here, and this becomes low, this transistor will turn off, therefore removing the path to ground and basically removing this capacitor out of circuit. Therefore, we're only operating on this 4.7 microfarad, which is then going to cause the flash rate to change to double rate. And that's it. And we notice also with the P connection, this TIP42C, going from the positive rail through the emitter, being driven off of the collector of the driver transistor for the relay, which stops those little blips that you see on the globes when the P connection is first connected or disconnected, where both globes will light up for a few milliseconds or so. So that fixes that problem. And that's it. I'm going to update this in another video later. I just want to get this video finished. This will probably change, but I'll probably have to modify over here this resistor network in order to see the current flowing through, say, a 15 milliohm shunt. The original circuit, which is linked in the description, uses a 30 milliohm shunt, but I couldn't actually find one online. And the 15 milliohm shunt's 15 millimeters long by 1 millimeter in diameter and bent at right angles at each end. So you can imagine a 30 milliohm shunt resistor wire would be twice as long. We were looking at like 30 millimeter, which on a PCB would take up quite a fair bit of its real estate space. So I don't really want to use a 0.33 100 watt resistor for the shunt because, well, it would work and be plenty powerful enough to handle the current that would be flowing through the circuit, which is approximately 4 amps with two 21 watt globes and a 5 watt globe as a side marker, either on the fender or on the tip of your rear view mirrors. Just fine, because it's only going to be a maximum of 50 watt there, so it's only half the capacity of this particular shunt resistor. Now, I've got a 2 watt device in there, and it does get pretty red hot, even flashing at the fast rate, after about 30 seconds, and after about a minute you can't even touch it anymore. So yeah, there's just way too much current flowing through there for it to handle. So it has to be changed to a proper shunt, because those shunt wires that I was talking about and showed a picture of just before this schematic, they're good for handling up to about 10 amps of current running through them anyway. So yeah, I've just got to get it to work with this comparator circuit. So I will be looking at that in another video once the parts arrive and see if we can get this to operate with a shunt wire instead of what I've got. That'd be good. And anyway, so I'm going to leave this video here. If you enjoyed it, please remember to go down below, rate, comment and subscribe if you haven't done so already. And this is the Astro 30 saying, have a great day. I'll see you in the next video. Thanks for watching.